Picture a photograph slowly dissolving into television static until every trace of the image is gone. Now imagine running that backwards, static reassembling itself into a sharp, detailed picture that never existed before. That reverse move is exactly what a diffusion model learns to do, and it is the engine behind Stable Diffusion, DALL-E, and Midjourney. Sounds like magic, but the idea underneath is surprisingly humble. You teach a network to undo noise one small step at a time. Let's break it down. Look, the whole thing has two directions, a forward path that destroys and a reverse path that creates. We follow the journey one stage at a time. Start on the left with an ordinary training photo, a real image the model gets to study. Nothing has happened to it yet. This clean picture is the destination we eventually want to reach, so hold it in mind as our target. Now the forward process begins. Step by step, we sprinkle a little Gaussian noise onto the image again and again, until the picture is buried and only pure random static remains. Here's the neat part, this destruction needs no learning at all. It is purely mechanical corruption. Here is where the network earns its keep. We hand it a noisy image and ask a single question: what noise was just added? By learning to predict that noise accurately, the network quietly learns how to remove it. A U-Net architecture usually does the heavy lifting, and remarkably, that single, simple objective is all the training really needs. Finally, the reverse process runs the whole thing backward. Beginning from pure noise, the trained network strips away a little at each step, and slowly a coherent image emerges from the chaos. Apply the denoiser enough times, and structure appears where there was none. So why did diffusion quietly take over image generation? Compare it against the approach it dethroned. A generative adversarial network tries to conjure a finished image in a single shot, while a rival network judges it. That contest is powerful but notoriously temperamental, prone to unstable training and mode collapse, where it produces the same few outputs and quietly ignores the rest of the data. The diffusion approach refuses that all-or-nothing gamble. Instead, it takes many gentle denoising steps, each one an easy, well-defined prediction. Training stays remarkably stable with no adversarial game to balance, and the payoff is astonishingly high-quality, diverse images. That trade, patience for stability, is why diffusion quietly conquered the field of image generation. Strip it back, and three ideas explain why diffusion models matter. The first idea is the reversal itself. A diffusion model learns to undo a gradual noising process, turning the daunting task of creating an image into a long series of tiny, manageable denoising steps that ordinary hardware can chew through. The second idea is stability. Because training just means predicting the noise added to an image, there is no adversarial tug of war to balance. Diffusion trains calmly and reliably, sidestepping the mode collapse that haunted GNs, which is precisely why it overtook them. The third idea is control. Diffusion models are easily conditioned, so a text prompt can steer the denoising through cross-attention, giving us prompt-driven image generation. The main cost is speed, since sampling needs many steps, though tricks like DDIM and running in a compressed latent space help a lot. Alright, let's lock in what matters. A diffusion model generates images by learning to reverse a gradual process that adds noise, turning pure random static back into a coherent picture. The forward path just destroys, adding noise with no learning, while the neural network learns the reverse path by predicting the noise so it can denoise. It matters because diffusion trains stably without adversarial games or mode collapse, producing high-quality, diverse images, which is why it took over image generation. Conditioning on a text prompt through cross-attention gives us prompt-driven images, and its one real weakness, slow sampling, is steadily being solved. Hungry for more AI ideas explained without the jargon? That's our whole mission over at Standarity.com. Come explore with us.